everyone, welcome to Physics 1, Lab 2, Motion of a Falling Object. Today, we completed an experiment to observe an object that is dropped from rest and falls somewhat slowly. We examined Newton's second law, or the momentum principle. We do this by observing the effect of gravity and drag force on the object that is dropped. We also use velocity and position update formulas in this experiment to construct our graphs of our findings. So there's the velocity update formula, the position update formula, and then Newton's second law, which basically states that net force is proportional to the change in momentum. So the purpose of this lab is to observe the actual motion of a ball dropped from rest and then compare it to two computational models. One with only the force of gravity acting on the ball, and then one with both gravity and drag force acting on the ball. So the main results of this lab show that our actual video that I put into Tracker shows that the ball's velocity continues to increase at an increasing rate in magnitude as delta t increases. All of the velocities are negative because I chose downward as a negative y direction. And then in our first computational model, which is the one with only gravity, as velocity increases, the velocity also increases, but it's at a constant rate. In the second computational model, which is the one with both gravity and drag force, the velocity follows a similar pattern to the first model, where the magnitude of velocity increases at an increasing rate as delta t increases. And in this experiment, the system is the ball and the surroundings are the floor, and my friend Sophie's hand, who is the one who dropped the ball in the video that I will show soon. Okay, so here's our first relevant model. This is the actual video, and here is the position versus time graph. The initial position of the ball is 0, 0, 0, or specifically in the y direction, y equals 0, and then the velocity of the ball is also 0, 0, 0, and in the y direction, 0 meters per second. And on the right here, I just have all of our data points for position, time, and then velocity in the y direction. Here is our second relevant model, which is the position graph without drag force. And this was the computational model. And on the right there is the code that I wrote to run this. And then our third relevant model is the position graph with drag force and gravity, also created through the code. Okay, so here is the actual video of Sophie dropping the ball. Our relevant questions for this experiment were which models, if any, predict a terminal velocity. So if I had chosen a larger time frame and we also dropped the ball from a higher point, you would be able to see on a velocity versus time graph that the first and third models would show that the velocity eventually becomes constant and will not increase anymore. And by increase, I mean increase in magnitude, because it's always going to be negative, but eventually it'll become constant. So this can be also seen in the equation, because as the velocity and the drag force equation increases, it will balance out the force of gravity. The drag force constant is small, but the gravity increases linearly and drag force increases exponentially. So the net force would eventually go to 0, thus making the acceleration go to 0. And that means that velocity is done changing and stays constant. Our second relevant question is, imagine the ball was initially thrown downward. Would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? So if our object was initially thrown downward, the terminal velocity would take a shorter time to achieve, and it would still be the same terminal velocity as where the ball was dropped from rest. We would just have a smaller delta t to get there. And here's proof from the computational model. So these graphs basically show two test cases, one where the velocity is initially 0, one where the velocity is initially -1 meters per second. So as you can see in these graphs, both have a terminal velocity of around -7.8 meters per second. But in the first computational model, it is reached around 3.5 seconds. And in the second computational model, it's still around that range, but it's like slightly earlier. So conclusions and possible errors of this experiment: I could have definitely dropped the ball from a higher starting point to have more data points. Our delta t was quite small, so in the future, I would like to have more data points, a larger time frame, and start from a higher starting point. And also, we had to estimate the mass of the ball, so it might not all be correct based on what the materials that we used. And then a conclusion that I made is that the most accurate graph is probably the third graph, the computational model with both drag force and the force of gravity, because it puts the ball in perfect conditions while incorporating all the forces acting on the ball while it is in the air, and it doesn't account for possible errors, thus making it more accurate. So thank you so much for watching, and I hope you have a great day.